Okay, hi. In this video, I'm going to introduce a concept called the magnetic dipole moment that is going to be helpful to us in understanding how a torque can act on a loop that carries a current when you place the loop in a magnetic field. I'm going to start off not talking about currents at all, though, and I'm just going to start off by talking about a magnet. Let's imagine that say that you have a bar magnet. It's very strong. It has a north pole at the bottom and a south pole at the top. The idea would be, we know that that magnet creates a magnetic field in the space around it. And that magnetic field is going to be looking a lot like the field that we see from an electric dipole with plus and a minus charge. So for example, the north pole is like your positive charge, and so the magnetic field is going to go away from the north pole, and then it's going to wrap around, and it's going to come back into the south pole. And of course, this is a 3D picture, right? And so it's also happening here. In fact, it's coming out at us. The magnetic field fills up all space. Now, if you have a compass, which is supposed to be this circle here, your compass needle will align to this field. And really what a compass needle is it's a bar magnet. And what happens is that the north pole of this bar magnet will point in the direction of the field line towards the south pole. And so that the compass needle is actually a magnet, and it aligns with this outside magnetic field that's coming from the bar magnet. Okay? Now, the idea that we're going to introduce here is that you can talk about a vector which points from the south pole to the north pole, and we're going to call that the magnetic dipole moment, and it's a vector. Okay? The symbol that it gets is the mu symbol that we used for micro, and it's basically a vector that always points from south to north in a magnet. So mu, it's a vector, and it always goes from S to N in a permanent magnet, like a piece of iron. So the compass needle has a dipole moment which points straight up. In fact, the large bar magnet also has a dipole moment of its own. It's bigger, and it points down. And if you like, it's kind of like the continuation of the magnetic field lines, if you think about it that way, as if they would continue inside the magnet, which they really do. So why are we talking about this, in this case? The reason we're talking about it is because the outside magnetic field from the big magnet actually exerts a torque on the compass needle. And that's why the compass needle kind of snaps into place. Okay? And what's happening here is that the dipole vector of the compass is trying to align to the external magnetic field. It's trying to align. And that's why compass needles always point north, is because that they're basically trying to align, and there's a torque that acts on them. A little aside here, if you're suspicious about this, and you're thinking, well, wait a minute, I thought that the North Pole was up in the Arctic. You've been kind of misinformed on that. The Earth itself, if I were to draw it, has magnetism, of course, but the Earth's south magnetic pole is actually located in its north geographic pole. So in other words, Santa really lives at the South Pole, if you're talking about magnetism. If you want to find out more about that, you can just look in your book or look anywhere on that. But that's why compass needles, the North Pole always points up on a map. So it's just something to know. All right. So let's now make the connection to current loops. And so I'm going to try to do this kind of in 3D here. Sort of looks like a trapezoid. That is supposed to represent a loop. It's sort of maybe square-shaped. It's coming out at us. And it's carrying current, represented by this symbol I. And so what's going to happen here is that we are going to say that this current loop has a dipole moment that's associated with it. And that dipole moment is going to be a vector which is perpendicular to the plane of the loop. Okay? So this is a 3D picture, right? So you're looking at this thing as it's coming out at you, and now the magnetic dipole moment is coming out at you. If you were to look at it from a top view, it would be like this. In the top view, the dipole moment would be doing this sort of a thing, right, the point, and then the current would be doing this. So if that helps you, that's what the top view would look like. Now, that vector, how do you know which way to make it go? Do you make it point up or do you make it point down? You seem to have like two different ways of doing it. The way that you figure it out is using your right hand, using a different right hand rule. So the idea would be that I would place my thumb in the direction of the current. So my thumb is going to go to the right, and then my fingers will naturally wrap around that wire, and my fingers will pop up in the middle of the loop. And this is, of course, on my right hand. And so the magnetic dipole moment vector has to be pointing straight up in this case. Okay? So think about, I'll put a note here. So your thumb is I, that goes in the direction of I, and then your fingers become the dipole moment vector direction. You notice here this is a little bit simpler than the other right hand rules. We're not really using my palm at all. This is not a cross product thing. This is just like kind of trying to figure out the direction of one vector if you know another. So this is, don't worry about the palm at all. It's not that complicated. Okay? So basically grab the wire with your hand, your thumb goes with the current, your fingers should curl in the direction of mu. Okay, so this is how we define the direction of the dipole moment vector. We're going to define it fully with that relationship. And so we're going to say that the dipole moment vector is actually the product of the current in the loop, I, times the area vector. And so the area vector has got to have the same direction as the dipole moment. Okay, so these vectors have the same direction, and then we're just treating I like a scalar, which technically that's what it is. Okay. And the idea is that you want that vector to line up with the magnetic field. So if we have a situation where the magnetic field, let me draw this over here. Let's say that the magnetic field goes this way. So in the outside world, there's some type of a field. It's going straight up. It's already lined up with this. That would mean that there would be no torque. So this loop would not twist if the field was going straight up, because this vector and this vector had the same direction. What if the field was going this way? So in the outside world, someone turned on a magnetic field that goes from left to right. What would happen is that this vector, which starts off like so, is going to be twisted. And so you're going to have a torque which is in the clockwise direction. And it's going to make the whole loop twist around an axis, right, which passes through it. So maybe in this case, the axis would be like this. And the whole loop is going to kind of flop over so that you can line up the dipole moment with that magnetic field. So that's a clockwise torque. If you make B go this way, and you start off your loop going this way, of course what's going to happen now is that the torque is going to act in the opposite direction. That's going to be a counterclockwise torque. And so now the loop is going to be twisted kind of in the opposite direction. So what's nice about this is that you can look at a loop, and if you know the direction of the current, you can use the right-hand rule to kind of quickly figure out which way the dipole moment vector is pointing, and then you can compare it to the magnetic field, and you can see just which way the loop is going to turn. The other thing I'll say is that if you recall from our earlier video, we said before that the torque that acts on a wire loop is equal to NIAB times the sine of theta. That was our big formula from earlier, in the earlier video. I think I'm going to leave out the n for now. I'll just cross that out so that we'll talk about n equals 1. But you can see that what this actually can be replaced with is that we can replace I times A with the dipole moment. And so the current times the area of the loop is now replaced with the dipole moment, at least the magnitude of it. So you multiply that times B, which is the field strength, times the sine of the angle between them. So this is mu, and this is B. The angle that we're talking about is the angle between those two things. And if you really want to simplify the notation, you can write this as a true cross product. That's the way I like to write it, because that kind of captures the whole thing. So torque, of course, is a vector, and it's equal to the cross product of the dipole moment crossed into the magnetic field. Okay? So this formula down here is kind of an alternate way of expressing the torque that acts on a current carrying loop. It has built into it this new thing that we're calling the magnetic dipole moment. Why do we use it? Because it has a lot of value in allowing us to quickly figure out which way a loop is going to tend to twist when it's placed into a field. Also notice that the magnetic dipole moment is a vector. It points perpendicular to the plane of the loop, and we have to use the right-hand rule to figure out which direction it goes, because you always have a choice of up or down, or in or out. And so you have to use your right hand to figure out which way it actually goes. So that's the concept of the magnetic dipole moment. And in the last video, we'll just show you mathematically how it can help you to find the torque and also the potential energy of a loop in this situation.